Hi, colleagues. Let us start today's talk titled Behavior Modeling via Reward Learning and for Autonomous Driving. Today we have Erdem Biyik, and he is fifth-year PhD candidate, and now it's already successfully defended, in fact, in the Electrical Engineering Department, Stanford. He has received his bachelor degree from Biyik University, Turkey in 2017, and master's degree from Stanford University in 2019. He's interested in enabling robots to actively learn from various forms of human feedback and designing altruistic robot policies to improve the efficiency of multi-agent systems, both in cooperative and competitive settings. He also worked at Google as a research intern in 2021, where he adapted his active robot learning algorithms to recommend the system. He is now moving to Center for Human Compatible Artificial Intelligence, CHAI, at UC Berkeley as a postdoctoral scholar, and will join the University of Southern California as an assistant professor in 2023. So let's welcome.
Thank you very much, Alexander. I'm excited to be here, and as Alexander introduced, I'm currently a fifth-year PhD student, graduating soon. And today I'm going to talk about some of my works in my PhD about how we learn from humans and how can we use that for multi-agent systems or human-robot interaction. So in my research, I work on, as I said, human-robot interaction and multi-agent systems, and this captures many different fields, such as human-robot collaborating together on some task, for example, stacking a burger or building a structure together, or assistive settings, such as an exoskeleton helping a person walk, or larger multi-agent settings where we have a number of autonomous cars interacting with a large number of human-driven cars. In all these domains, it's important that the robots or the assistive exoskeleton or the autonomous car, they should be able to model the behavior of other agents to make their interaction with them more efficient. So how do we achieve this? Maybe machine learning is the answer. So we have seen this as a successful approach in many domains. We just need to collect some large data sets, and then we should train a large model, and it will do this behavioral modeling or maybe even more for us. For example, there's OpenAI GPT or GPT-3, which has been trained using 45 terabytes of text, and it was able to model how humans use language, or it was able to, let's say, produce human-like texts. Or there's ImageNet. It's a data set of 14 million images, and it led to very successful image recognition models. There's AlphaZero, which achieved superhuman performance in chess just by playing 44 million chess games on its own. But what is the state in robot learning? Today, the state of robot learning looks like this. This is a video from Google's ARM Farm, where we are seeing a few robots working non-stop to learn hand-eye coordination. But compared to millions of chess games every day, this is almost nothing. And the problem gets even more difficult if there is a human in the loop, like in the human-robot interaction task, because we need people to sit in front of these robots and interact with those robots, maybe control them, maybe give some feedback, and that's just too expensive data. So I claim to be able to have robots or AI agents in general model, to make them model human actions, we need algorithms that will learn from humans, that will learn from humans' feedback with as little data as possible. So today I'm going to talk about this and some applications of behavioral modeling in autonomous driving, and I'm going to divide this talk into 3 parts. First, I'm going to talk about how we learn from human feedback. Specifically, I will focus on learning from comparisons. So the robot is going to be interacting with the human, and it's going to ask questions, comparison questions, and based on human's feedback, it's going to learn what the human wants. And then to improve data efficiency, I'm going to move to the second section, which I call active querying. Here, the idea is, as I said, in robotics or human-robot interaction, more specifically, data is very expensive. So we need to find ways to collect the most useful data. So it's an active learning problem where now the robot is optimizing for what questions it should ask to the user. And finally, I will move to the last section in which I'm going to show some examples of how behavioral modeling can help us in autonomous driving. And specifically, I'm going to talk about how modeling the attention of other drivers make us predict their actions or trajectories better. So let's start with how we learn from human feedback in robotics. And so one way to learn from humans, and I think this is the most commonly used way, is to learn from demonstrations. So in this approach, the user or the human, they just give some demonstrations to the robot, and based on these demonstrations, these near optimal demonstrations, the robot learns what the task is or in what way the task should be solved. This is a very popular approach, and for example, there's behavioral cloning. It has been around for more than 30 years. And it has been successfully deployed in many applications, or maybe I should say developed instead of deployed. But usually we needed additional components on top of learning from demonstration methods. For example, in our virtual in the middle, we had to learn multiple policies and then how to optimally switch between them. Or in the one on the right, they had to add additional safety controllers on top of imitation learning. So what is wrong with these methods? Why can't we just imitate a human and have a perfect driving policy? So to see that mathematically, or maybe before that, the reason why learning from demonstrations may fail is that we are trying to imitate humans, but humans are not optimal. So to see that mathematically, let's say we are given a set of demonstrations, which I denoted D here. So each psi variable here, they're basically trajectories. So psi1 is one demonstration by the human, psi2 is another demonstration. Okay? And let's say we have some trajectory features. So each trajectory maps to a set of features. In the case of autonomous driving, this could be maybe the minimum distance to the other cars, the car's average speed, maximum speed, which lane it's going, those kind of features. So here I'm using an example from robotics or manipulation. So we have a robot trying to reach this notebook on the desk without colliding the obstacle. So for example, in this case, the features could be its final distance to the notebook, its minimum distance to the obstacle, its average speed, etc. And the assumption that we are going to make, and that we are most of the learning from demonstration methods will do, is there is a reward function the robot needs to optimize, and this reward function is a parameterized function of the trajectory features. So essentially what I'm trying to learn is these reward parameters W.
But this formulation seems to be more like reinforcement learning instead of imitation learning.
Yeah, this is more like inverse reinforcement learning, because there are some demonstrations, and based on those demonstrations, I'm trying to learn the reward parameters W. So yes, I'm not trying to directly learn a policy. Instead, I'm trying to learn a reward function. So one solution to this is an approach called Bayesian inverse reinforcement learning. And the idea here is that, as I said, I need to learn these reward function parameters W. And how do I do that? I keep a posterior for that. So this probability of W under the demonstrations. And I want to find, for example, the maximum a posteriori W, or maybe I can take its expectation. So how do I do that? I first use Bayes' rule. The first term here is just prior, so I can use uniform distribution, or if I have some domain knowledge, I can put it into the prior. The important term here is the second term, because that's going to incorporate the information from demonstrations into the model. So the first assumption we make is that each demonstration is conditionally independent. So given the reward function, the demonstration of a human does not depend on earlier demonstrations. This is a reasonable assumption. That's fine. The second assumption we need in this model is a model for how humans give trajectories, or how humans give demonstrations. So in this case, in Bayesian inverse reinforcement learning, the assumption is humans are more likely to give demonstrations that are near optimal. So the probability of a trajectory is proportional to exponential of its reward. So that's like a softmax rule, or in some cases, like if it's a choice model, it's like it's a logic model. And this is trying to capture some like noisy behavior of the human. So this allows humans to make some mistakes. Like we don't need all actions to be optimal. We allow some slackness. We allow some suboptimal actions. But still, this is problematic, and this is where Bayesian inverse reinforcement fails, because this model assumes the most likely demonstration is the optimal one. But for example, in the picture that I'm showing here, it's the optimal trajectory, but there is no way a human is going to be able to teleoperate this robot to move as smooth as this. And in fact, this robot is just so difficult to control because it has high degrees of freedom. Here you are seeing my lab mate, Andy, and Andy has a lot of experience with this robot. He's trying to basically solve the task that I described using a teleoperation interface, and he's having a hard time. And in fact, at the end, the robot gets stuck in that configuration without reaching the notebook. And this is not the only reason. Like teleoperation is not the only problem. Humans have these biases that prevent them from taking optimal actions. For example, there is this work from UC Berkeley where they showed humans do not like their own driving demonstrations. They think it's too aggressive. And like we recently showed humans consistently take suboptimal actions when they encounter situations that involve risk. Like this has been studied in behavioral economics and cognitive science, and there are like many different examples of how humans may fail to find the optimal actions or may fail to give like near optimal demonstrations of Java. So if demonstrations are not optimal, then how can we even hope to learn from like these demonstrations? Like we are not going to learn an optimal policy. So our idea is to use a different interface, and in this interface, we want the robot to show some demonstrations, show some trajectory to the human, and then the human user is going to evaluate this demonstration. But this is also not a very easy task for the humans. And it might not be obvious why, but let me ask you a seemingly unrelated question. So, how dark is this blue?
Not as dark.
Not as dark. Okay. Yeah, not as dark is a good answer, and I think that's one of the like most common answers. But not as dark is it contains some amount of information, but at the same time it's very ambiguous, because when you say not as dark, I don't know what's your reference point for a dark blue, right? So similarly, if I ask a user how good this robot trajectory is, they will tell me maybe not as good, or maybe they will say like it's okay, and it's going to be very ambiguous and it's going to be hard to learn. Instead, if we introduce a second option, in this case a second color, and ask which blue is darker, now everyone is going to give the same response, and it's going to be very reliable. So I can more reliably learn from comparisons than like evaluations of a single demonstration. And we are actually generating comparison data all the time. For example, every time we make a selection in Uber or Lyft, it's a comparison data about like our price latency trade-off, or maybe about comfort. Or every time we click on a YouTube video, it's a preference over the other options. And sometimes our actions implicitly generate comparison data. For example, Google Maps gives us multiple navigation options, and then we take one of them. And Google then understands our preference about maybe transportation mode, maybe latency, etc. So our idea is to use comparative feedback to learn reward functions from humans for robotics. So in this first section of the talk, that's what I'm going to talk about. So what is comparison data in robotics? As I said, we are going to have the robot demonstrate multiple trajectories to the user, and then we are going to ask the user which trajectory they prefer. And based on their response, we are going to fine-tune our posterior about the reward function. So how are we going to do that? Let's bring this formulation back. Now we are going to have a second data set, which is the comparison data set. Here, each data sample is a tuple. Basically, the psi A is the first trajectory that I show to the user, psi B is the second trajectory that I show, and then Q is a binary variable that says whether the user preferred trajectory A or B. And I'm going to have multiple such comparisons. So I need to now put this into the Bayesian inverse reinforcement learning framework. I had this posterior distribution. Now I have a second data set, so I need to condition on the comparisons too. The first assumption I'm going to make is like similar to the assumption about demonstrations. Like demonstrations and comparisons are condition independent from each other if I already have the reward function. And similarly, each comparison is condition independent. So when I answer a comparison question, it doesn't depend on earlier comparisons that I make, as long as I know the reward function. Now, the final assumption, the softmax assumption, it's still here. So I'm assuming the user is more likely to choose the good trajectory over the bad trajectory. But now it doesn't hurt us here because it's not the humans who teleoperate the robot anymore. We don't expect them to like demonstrate us good actions. We don't expect them to have good muscle memory, or we don't expect them to like optimize for long horizons. Instead, we are just showing them two different trajectories, and they're choosing which one is better, which is a like strictly easier task for humans. And at the end, we have this like expression in the bottom line, and it's basically an unnormalized posterior. So if I maximize this with respect to W, or if I take an expectation over this, I'm going to have a point estimate of W, which is the reward function that the robot needs to optimize. So
Question. So if do we still need the D there in this case?
No, so we can. That's a good question. So if we don't have any demonstrations, we can drop all the D terms in this formulation and basically the black text in the last two lines, and we can learn like solely from comparisons, and it's fine. Sometimes the problem is comparisons contain very little information. Like when we are looking at trajectory A versus trajectory B, the most we can get is 1 bit of information because it's just a binary choice. Whereas in demonstrations, we get information about multiple states, about the like optimal actions in multiple or near optimal actions in multiple states. So if data efficiency is a problem, going for only comparisons might be difficult. And that's why we usually start the algorithm with some demonstrations and then add comparisons on top of it. So demonstrations are biased, but if we start with a small number of demonstrations and then add comparisons onto it, we can also get rid of those biases.
So the demonstration is still coming from human in this case?
Yes.
Okay, so that makes sense.
So yeah, demonstrations are optimal, but they're good for data efficiency. So here is an experiment that we did on a similar task. So we changed the obstacle location, and because we are doing reward learning, it's fine. It can optimize any policy for every set of like obstacle or goal. And in this case, the robot is trying to reach the Pringles box. On the left, we have 5 demonstrations with Bayesian IRL, and on the right, we have 1 demonstration plus 15 comparisons. You might wonder why like 4 demonstrations correspond to 15 comparisons. The reason for that is the way we try to make this fair is that we chose the number of comparisons such that in simulations they have the same convergence rate. And you can see that on the left, Bayesian IRL, it's trying to avoid the obstacle like very harshly, and at the end it gets stuck in a weird configuration. And the reason for that is when we look at the reward function that's learned, it like overemphasizes avoiding the obstacle. And to make sure it avoids the obstacle, it gives up on the actual task and it doesn't reach the Pringles box. Whereas ours reach the Pringles box, and at the same time, it also doesn't with the obstacle. So with comparisons, we were able to like fine-tune this reward function to achieve the task.
So I have one question.
What are the
planning purpose?
just curious, what are the comparisons in this specific example?
So what are the
15 comparisons?
Yeah, those 15 comparisons are they're generated by humans. So in the next section, I'm going to talk about how we generate the questions. So the robot generates the questions in some specific way that I'm going to talk about, and then a human user who knows the actual task, like who knows that we are trying to reach the Pringle spikes and avoid the obstacle, responds to those questions, like gives binary responses.
I see. Would that be a more fair comparison if we use one demonstration plus 4 comparisons? So the total number is equal to 5 compared to the left. I don't know.
Yeah, it's difficult to like satisfy fairness here because giving a demonstration is much more difficult than giving a comparison. So if you are, for example, looking at the cognitive load we like give to the humans, then it makes sense to have more comparisons than demonstrations. But if you are, for example, looking at the time it takes to generate this data, maybe then you're right, we need like fewer comparisons. And as I said, what we did is we just took the number of comparisons that will make the convergence rate the same in simulations.
I see. Thank you.
Yeah. I think here is like, you show this robot arm. Maybe, like because human is not, it's not very intuitive for human to demonstrate, right? But I think like you also mentioned like for driving, for example, it's relatively simple kind of task. If you give like a very clear driving guideline, right? Like you should drive like this, like having some rules. I think like human can probably provide a very good demonstration, right?
Yeah, I think in general, humans like I think in driving it's true that our demonstrations are much better than how we would demonstrate a robot like this. But there are again some certain cases or like certain biases that will make us like not like the driving demonstration. So as I said, there's this work from UC Berkeley, and what they did is they collected some driving demonstrations, and then I think a week later or so, they basically like put the people in some simulators and they replayed their trajectories to them back, and they said, oh, this is like the autonomous driving, and like, do you feel comfortable being in this car? And they said no, because I think in general, people like when we have control as a driver, we feel okay. But if we're in a car that's driven by someone else or that's driven by a robot, then we want it to be more cautious, we want it to be more timid. So I think it's a question of like, are we trying to make the cars human-like, or are we trying to make the cars drive in a way that humans will like? I think there is a difference between the two.
I think like that might be a problem if you're driving in simulation, right? But if we ask human to drive in real world, that might be fine.
No, then I think it's still a problem. Like imagine you are driving a car yourself and you are in rush, so you can make some speed and you'll still feel okay. But imagine you are in a taxi and the driver is like is going faster, right? And then you are not going to feel as safe as you would do if you were driving on your own.
Yeah, but say for example, like if we are talking about like the having some guideline, right? Like clear guideline, like these are you have to follow the rule, you have to drive like this, and with some training, like maybe human can.
Yeah, I think assuming
obey those.
Yeah, assuming humans will obey the guidelines, I think it's possible. I think there are still some problems about, for example, like long horizon planning. Like when you do lane changes, you usually do lane changes based on the, I don't know, maybe like next 50 meters that you see or something, or maybe the next, I don't know, 10 seconds that you enter. Whereas with a robot, you should be able to plan longer because you don't have, like, you have more competition. So I think there are these like certain biases that will, as I said, in the autonomous driving case, I think the differences might be much smaller. But I think there are still cases where we have like suboptimalities. Okay, so we have a question.
I ask, how do you handle inconsistent comparisons?
Yeah, inconsistent comparisons. Yes, good question. So this this softmax model, this if you look at the last line, this orange part, it allows some mistakes in comparisons. So although it should be minority, in a small number of questions, the user might give incorrect answers, and it's fine. And this is coming from discrete choice theory. So in discrete choice theory, the assumption is when you are presented with a set of discrete options, you are like the probability of you choosing an option is proportional to its utility. In this case, the utility is the reward function or the exponential of the reward function, but we are not making suboptimal demonstrations have zero probability. We still give them some weight. So inconsistent comparisons are fine as long as they do not like dominate the data set.
How did you select the trajectories to compare? Is it just random, or do you do like active?
Yeah, good question. And we do active. So yeah, let's talk about that. So the key takeaway of the first section is that humans are better at comparing than demonstrating, especially in like robotics and manipulation tasks. And robots can learn from these comparisons. And in fact, they should, because we have this huge data problem in robotics. So we should utilize all possible sources of data. But the issue is, yeah, we still haven't solved the data problem. Like, let it be demonstrations or comparisons, we don't have large data sets. So we should optimize what data we are collecting. And this is exactly like what you are asking. So how do we decide these trajectories that we show to the user? And this is why in the second part, I'm going to talk about active querying, where like we look at how the robot comes up with trajectories that it will ask the user. And it's an active learning problem. And if you're like active learning has been studied both like practically and theoretically in the machine learning and robotics domains. And like if you're working on machine learning, if you did some like research on active learning, you might be familiar with these kind of plots where in orange we see active learning and in blue is the random data generation. And you might think that it's a very like small marginal difference and active learning doesn't give any practical benefits. But that's not true in robotics because in robotics we have this, as I said, huge data problem. So we are particularly in the low data regime. And also active learning can help us elicit more reliable human feedback. So by optimizing what question I ask to the user, I can make sure the human gives me more reliable feedback. And because of this, it has attracted attention in the robotics community a lot. For example, there is this work by OpenAI and DeepMind in 2017, where they were able to teach these unusual behaviors to these simulated robots by using a few thousands of comparison queries. Or there's this work from Berkeley where they proposed a comparison-based reinforcement learning algorithm. And you might notice that we are trying to solve a similar problem here, similar in the sense that we are trying to learn something from comparisons. But there is an important difference when we are working with real robots, and that is we cannot really make thousands of queries. A human is going to answer these questions, whereas in these works, it was usually on the scale of thousands. And because of this, we are going to do active querying to minimize the number of questions we need to ask the user. So how do I choose queries? One method is called maximum volume removal. So the important difference is in demonstrations, the user gives trajectories to the robot, and we have control over nothing. It's the user who decides everything. Whereas in comparisons, the robot shows two trajectories to the user, and then the human responds. So now we have control over what trajectories we are showing, so we can optimize them for example, data efficiency. So in this maximum volume removal method, what we do is we start with this posterior. So we assume, we don't need to assume, we can start with any distribution, but let's say we have this posterior distribution conditioned on the demonstrations and comparisons that are already collected. And now I'm going to ask one more question to the user to better converge on true W. Just for visualization, let's say my W space is two-dimensional, and these are the samples from this posterior. So these are basically my hypothesis for the reward function. And let's say I'm going to evaluate how informative this query is, this query of two comparisons. So each of these hypotheses of like W samples, they're going to give me a probability for the user's choice. So they're going to estimate what the user is going to choose. And in this case, this query doesn't look very informative because we almost already know the user's answer. Like it's very unlikely that the user is going to choose the trajectory on the left, the one with the green border. Okay. And this means I'm not going to be able to remove a lot of hypotheses from my hypothesis space after I update this posterior distribution. Instead, let's say there is this other query, which gives maybe like more diverse set of probabilities. And it makes more sense to make this query because if the user chooses the, for example, orange trajectory, then I will be able to remove a good amount of hypotheses from my hypothesis space. Like I'm going to eliminate the ones that will give more probability to the green trajectory or the trajectory on the left. And similarly, if the user chooses the trajectory on the left, I will do vice versa. So what maximum volume removal is trying to do is to, like, as evenly as possible, like divide these probabilities on the two trajectories. So we implemented this, and it gives some like practical gains over random querying in terms of data efficiency. Here, the y-axis is a measure of how well the true reward function aligns with the learned reward function. So these are from some simulated studies. They include a driving simulator, simple like 2D driving simulator, some environments from OpenAI Gym, and some from Nuro. These are robot simulators.
What was the mathematical division between these two? Is it literally like trying to make the weight as close to half as possible? Is there some like conditional entropy term using?
Yeah, conditional entropy is going to show up next, but what's happening here is that it tries to maximize the minimum probability on one of the sides.
I see.
So it's kind of like it's literally trying to make it 50-50.
Yeah.
Yes, the question was from this previous slide. Yes, but for example, to have this distribution of choices for human, we need to have some sort of model. For example, how to know in advance before showing to human how they will choose, for example, one or another solution. So how do you?
Yeah. So how we do that is okay. So we start with we are trying to optimize for trajectories, right? So I generate these trajectories. I do not show them to the user yet.
Yeah.
It's just computation. I generate these trajectories, and I have this trajectory feature function like that gives me the features, and I also have this distribution that I have for the human. Maybe I didn't collect any data yet, so maybe it's just my prior. But I have a distribution for the human, and I can take samples from that, and each of those samples. So these like blue dots here, each of those corresponds to a reward function. So for the trajectories that I have in my query, I can calculate the reward under that reward function. And then based on that reward function, I can again use this softmax model to model the probabilities. And that's why like each of these reward functions corresponds to a different distribution.
But how do you avoid the degenerate case where the trajectory are similar? Yeah.
Yes, great question. So, yeah. So what we said is the trajectory on the right, we said it's a good one because it's almost evenly distributes the probabilities, and it would be even better if it were like this, right? But what if we have a query where we are showing two identical trajectories to the user? Because this would mean the probabilities will be evenly distributed because for each of the reward functions, it will be 50-50, it's just identical trajectory. And like from maximum volume removal's perspective, this is an optimal trajectory, this is an optimal query. But in fact, it's not going to give me any information because the user's choice will be just like random. And yes, this is the drawback of maximum volume removal. And maximum volume removal works in practice, like not despite the non-convexivity, but because of it. So if it finds global optima, it will actually create terrible queries. But because of local optima, it works. And we realized this, and we said, okay, this objective is wrong. We should change this. And that's where this conditional entropy term comes into play. So instead of maximizing volume removal, we said we should maximize mutual information or information gain. So now we are trying to maximize the mutual information between the user's response and the reward function that we are trying to learn. Okay, conditioned on the data sets that we collected so far and the query that I'm going to make. So equivalently, I can write this as the difference between two entropy terms. Here, the first entropy term models the uncertainty of the robot because it's conditioned on the data that I collected. And I'm still trying to maximize this. I'm still trying to come up with questions where the robot is uncertain about because it's going to give me a good amount of information. And the second term, it models the user uncertainty because it's conditioned on the reward function W. So given a user model, how uncertain the user is going to be. And I'm trying to minimize this because in this way, the data that I generate will be more reliable. Humans will give me like less noisy responses. And like if you look at these two example queries from the previous slide, you can see that for both of them, model uncertainty is maximum. My model doesn't know which one the user is going to choose. But for the left one, the user uncertainty is also maximum. Because for each reward function, the user will be like 50-50 between the two options. Whereas for the second query, the user uncertainty is minimum because given a user model, given a W, it's going to be 100% orange or 100% green. So in this case, the mutual information maximization is going to choose the second query as opposed to the first one. And in fact, when we implemented this, it's outperforms volume removal, and it was able to learn the reward function with an as few as like 30 queries as opposed to 100 in the previous results. And this is like, in these experiments, we don't have any demonstration. So alignment starts from 0. We have no information about the reward function. And then like within 30 queries, we learn the reward function. But in this case, I should admit the reward functions that we are trying to learn, they're like simple reward functions. We have low number of features. And here are some trajectories from our user study. So as you can see, volume removal generates like very similar trajectories, and that's not reliable information from humans, whereas the mutual information, it will generate a more distinguishable query, which is much easier to answer for him. Because like it takes the user uncertainty into account while optimizing for queries.
Can I ask a question? So it seems like a very good and universal approach, not only for example, demonstration of human robots, for example, when we are just making these queries about comparisons, what is better. It's in fact this maximization of mutual information, good choice. Have you tried to, I don't know, to use it for other tasks, not only for human robot demonstration?
Yeah, that's a good question. So I mostly tried it for robotics tasks, but like I did an internship last year at Google, and what I did was basically to try these algorithms for recommender systems.
Mm-hmm.
So it was like, let's say I want to make movie recommendations to the users, and I want to make this query such that I learn a lot about the user. I learn about, for example, the movie types or the movie lengths or the actors that they like, etc. And in that case, it again makes sense to maximize the mutual information between the user model and the slate of movies that we show. Mm-hmm. It's a slightly different problem though, because in recommender systems, it's also important that we show them a good set of movies. Whereas in this case, it's okay to show two suboptimal robot trajectories and ask which one is better, because the purpose of the human is to teach the robots. It's not trying to use the robot while in the learning phase. Whereas in recommender systems, we need to optimize both. So we had to go for like more multi-objective optimization types. But yes, information gain again works in recommender systems too. There are some other applications that I can talk about. For example, I worked on, instead of doing binary choices, can we ask the user to quantify their uncertainty. So let's give them a slider bar, and they will move the slider bar to one side, depending on how much they like one trajectory over the other. And this contains more information than a binary choice, and it increases data efficiency. I did some work for traffic routing. So this is like macroscopic level traffic routing. So imagine we are Uber or Lyft, and we collect data from the customers about like which routes they want to take, or like which like how fast they want to go, like are they okay waiting for paying less, etc. And after we get this comparison data, we learn models of these users, and then we use those models to optimize the traffic. Like we are trying to minimize congestion. And in this case, these like comparison learning methods again work well. And finally, I did some work for exoskeleton gait optimization. Here, the users of these exoskeletons, they're usually people with paralysis. So there is no way they can give us demonstrations. So they wear these exoskeletons, and we set the gaits for them, and then they experience walking with those exoskeletons, and then they tell us this one was better than the previous one, or this one was worse. And based on this, we learn the most comfortable and the safest exoskeleton gait for them. So yeah, the key takeaway of the second section is that depending on our objective, we can use different acquisition functions, different optimizations for what questions we ask. And if our goal is to minimize the number of questions that we are going to ask, it makes sense to ask questions where the robot doesn't know the answer, what the human user does. So yeah, I've been saying like we need to learn reward functions, and I presented a specific way of learning it, like learning from comparisons and generating questions for it. But then, if you go like one higher level, do we really need to learn reward functions? Like, why are they useful? So I think one like very straightforward application is that if we learn reward functions, like let's say I have a robot and I have a human, the human wants the robot to solve some task, so they have a reward function in mind, and the robot doesn't know that. So they interact, demonstrations, comparisons, the robot learns the reward function. Now, using this learned reward function, I can deploy this robot in the world, and then I can ask it to come up with a policy that will solve some task. Like this is the most straightforward application of reward learning, and we tried this on a bunch of different environments. In robotics, it was usually okay. We tried it on an autonomous driving setting, and we failed. So here is a setup. This is from a Carla simulator, and we created some near accident scenarios. In this case, I'm going to wait until it loops. Oops, didn't loop. So here we have a car, and there is a wall on the right. And because of that wall, the car doesn't notice the blue car until this point, and then it needs to brake very hard, and then it's going to conjure. So we created such like scenarios, and we tried to first learn a reward function and use reinforcement learning to come up with a policy for that. But we failed, and two main reasons why we failed is that in autonomous driving, the action space, it's a continuous space because of the steering angle and the like throttle, brakes, etc. And it's also, the horizon is not very short. Like if you're making decisions every 100 milliseconds, like this video is what, like 13 seconds. So that means like 130 decision points. And it's a very like difficult optimization, even for this like single scenario. And if you're trying to learn more generally a driving policy, there will be a lot more scenarios. So reinforcement learning algorithms, they kind of frustrated us. So we said, okay, we should do something else. And as I said, we were specifically looking at difficult near accident scenarios. And here's how I define near accident scenarios. We define phase transitions. So yeah, this is just describing the scenario that I mentioned. So a phase transition is basically when I change the state slightly, if I need to take significantly different actions, then I'm calling that state a phase transition state. So for example, in this case, the speed of the red car, if I'm already going fast, then I shouldn't push the brakes. Instead, I should go faster to pass the intersection before the blue car reaches the intersection. But if I'm slow, then I shouldn't be accelerating. Instead, I should push the brakes to give way to the blue car. So this is a phase transition state because depending on the speed of my car, the optimal action changes significantly. So there are different ways, and depending on the state, there are different ways of solving this. So one thing is, as I said, I can be aggressive and I can just try to pass this intersection before the blue car reaches, or I can be timid and I can just slow down and the blue car go, or I can just do a swerving motion to like avoid accidents. And the problem is like, when are we going for like which mode? Like if we do imitation learning is really good at imitating an aggressive driver or imitating a timid driver, etc. But the reason why imitation learning is good in this case is it's just learning a policy from these like states or observations. It's not trying to optimize for actions. It's not trying to solve this large optimization problem. But now the good thing is, if I have these different modes, these like aggressive mode, timid mode, or the swerving motion, then this means I'm actually discretizing the space. So I can use a reinforcement learning algorithm on this high level task. So reinforcement learning can tell us, okay, now be aggressive, now be timid, now do the swerving motion. And then the low level imitation learning policy will conduct those actions, execute those actions. And this is useful because, as I said, first, the action space is now discrete. It's much easier to optimize. And because this is a hierarchical RL setting, the high-level agent, it doesn't need to make decisions every 100 milliseconds. Maybe it can do decisions every 1 second. So it can say, for the next 1 second, use the aggressive policy. And then the low-level limitation learning policy, it can now take actions every 100 milliseconds because it's easier to execute.
So I have a question. So you said maybe like during training time, you can like have the your model to make, like slower decision, like every 1 second, for example. But like for inference time, I mean, like for online, right? Like if you kind of like, let the RL still like make this very slow decision, like say, if there's like pedestrian suddenly reveal, right? Like you still need to kind of like react to those. So if you like do this very slow response, would that cause issue?
Yeah, I think I think the answer is yes. If the decision making is slow, it will cause issues, like especially safety issues, as you said. But the nice thing about this is we don't need to wait until the high level agent makes the decision. So we can parallelize this entire thing. So I can pass the state through the RL policy and also the imitation learning policies, and then I can just use the RL policy to select which of these actions to use. So it's like parallelizable, and it's actually fast in inference time too.
I see. So doing some like selection, like action selection.
Right. Yeah.
How do you learn the IL imitation learner for the different modes? Like, do you explicitly say what is a mode?
Yeah. In this case, that's what we did. So we came up with some like hand designed classification rules about what is aggressive, what's estimated, what is swerving, and like these different modes. And we classified the human demonstrations based on that. But I think it's an interesting question, and I know there is some work by like Michael Koppendorfer where they do unsupervised clustering of these driving trajectories, and like in an unsupervised way, they are able to identify aggressive and timid behavior, for example. So there's a way to do it unsupervised, but in our case, we did supervised.
And then following up on Way's question, you can train with the like high level one every 1 second. Would you change that inference to be like faster? So like every 0.1 seconds, and is that a problem for generalization?
No, I think it's possible. So yes, you can train for you can train for longer horizons. So it's like you can train for 1 second decision making, and then you can execute for like faster decision making. I think it's fine. Like I don't see any problem evolving from that. But I don't think we tried it. So like empirically, I didn't test it, but I don't see any reason to make that problem.
Yeah, it's like, if you train in 1 second, right? Like if you select one action, it maybe the policy will learn to say expect you will follow this trajectory for 1 second, and then like if you deploy online, if you execute like every 0.1 seconds, would it affect?
I don't think that would affect, because like it's not like let's say there's an intersection, and it's not like every time I'm about to enter the intersection, I'm at a RL decision making point. It's like depending on where I start, the RL decision making points might be that point, or like 100 milliseconds earlier, 100 milliseconds earlier. So during training time, it's going to be exposed to all these different states. So I don't think it's going to be a problem. Like the decision making points will be already very diverse.
Okay. And so like for the modes that you mentioned, so you are like saying people can also using some unsupervised method. Do they like unsupervised clustering of pairwise of agents, or?
Yeah, there are. In our case, we did supervised, so we came up with these design rules. But yes, in the unsupervised case, you basically learn a latent state of the user based on their demonstrations. So, for example, those latent states might be like how patient they are. They don't have to be interpretable, but they end up being interpretable like this. And then you do like clustering on those latent states to basically cluster the trajectories.
Okay, so you're like projecting to using some CVE stuff, and then you try to do clustering in the latent space.
Yes. So yeah, high level policy learns the switching, and then low level policy imitates the user. So we have this set of like near accident cases. The first one is what I described, and then there's this wrong direction where this car almost adversarially goes into the wrong direction, and we need to either again accelerate or stop. There's this halting car. The car in the front just stops almost immediately. There's this merge where we are trying to merge between two cars, but depending on the blue car's aggressiveness, we might be able to merge in between, or we might have to wait until the blue car passes. Or there's, I think, famous unprotected left turn. So let me show you, for example, the merge case. So yeah, in this case, as I said, the car is trying to merge between the cars, and yeah, this case the blue doesn't allow that, but okay, we are patient. They're stubborn, and okay, here we go. So like here are some results. Like if we are, I mean, these are only the short clips from each result. But like if we are timid, then we wait until the blue car passes, and at the end we just merge behind the blue car. If we are aggressive, we just cut in front of the blue car. If we try to do, this is interesting, if we try to do imitation learning on this aggregate data, it fails. It completely fails because of this compounding errors issue. Like it ends up in states where it didn't see anything in the data sets because of these like multimodal data sets. But when we do this hierarchical RL, it kind of balances between things, and like I can show you some results. So like in the simulations, the aggressive one, it ended up being in a collision very often, whereas the collision rate was much lower for HL. And then there's completion time. If you are timid, sure, you are safe, but you are very slow. whereas again, H-rail gives a good balance. And based on the user studies, they liked H-rail. Like these are subjective ratings given by the users.
So would some people just say you need to like do data augmentation on your IL to make it work, and like you don't need the hierarchical RL part?
Yeah, I think. I mean, I think my view on this is like, why not both? Because I think hierarchical RL is useful for making things computationally easier. And I don't like, assuming reinforcement learning algorithms are reliable enough, I don't see any reason why we wouldn't use these hierarchical methods.
How do you like model other agents, and what is your reward here?
The other agents?
Yeah.
Yeah, we have hand-coded policies for them. Like hand-coded policies for them. So we make, so the green car, it just follows a fixed trajectory. Green car is not interesting. The blue car is the interesting one. So we hand code them to sometimes be aggressive and sometimes be timid. And that's like hidden. That's hidden from the ego car. So based on what the blue car does, it needs to decide whether it's like, for example, merging in front or waiting until.
So you just like have some model to control the other car. Is it also like a self-play kind of thing, or is it like a separate learned?
No, it's not really like it's not really a learned policy, because in this case, like it would be difficult to come up with a policy for the red car because it needs to do lane change and it's like its action space is larger. Whereas the blue car is just going on a straight line, straight lane. So we just need to hand code its speed, and that's like easier. So as a function of distance to the car in the front, we can come up with a simple policy, and that's what we did.
And the reward was also like hand designed, like how close are you to the right side, or like.
Yeah, we have those features. So like distance to the other cars, our speed, yeah, the distance to the lane centers.
How do you like make? I mean, like, do you only apply to this thing, simple one scenario, or like, how do you like scale to a lot of cases, right? Like,
we only did near accident scenarios, so it's not like general driving. So we only worked on these like near accident scenarios that I described, and that's mostly because of data limitations. Like we are a lab at Stanford. We're collecting data on our like simple simulators.
Yeah, no, like say
tons of data.
Say for example, like you have like this wrong direction. I mean, like you say, you handcrafted the blue vehicles policy or driving style, right? Like, but say for example, if you want to develop this in the real world, so like how do you make a scalable solution? Because it might be very hard to have human to identify it's a green car, which is blue car, and what kind of
Handcrafted policy is to use for other agents.
Yeah, so there are that's a good question. There are works on like generating like near accident data, but they're again simulated data. But like I think it's called test set generation. So it's like when you have a policy for an autonomous car, how are you going to test that for near accident scenarios? And there are works on like they basically do important sampling to come up with like challenging scenarios for cars. And I think those kind of works would be useful here to come up with these policies. But yeah, it's not like it's kind of like beyond the scope of this, because here we are just interested in the learning algorithm.
Okay.
So yeah, like learning rewards is useful for doing RL, and it's also like useful for modeling behavior. And in this case, I'm going to talk about not learning through reward functions, but like if we learn the attention of other agents, how can this be useful for us? So imagine a scenario where like let's say this is this car in the bottom. Let's say it's the ego car, and it's trying to drive basically, and I think we can agree that if it was able to predict what other agents are going to do, it would be useful for this car because it would better optimize its own trajectory. So how do we do that? We need to like learn models for other agents, and there's a line of work called like social LSTM or social attention, and it was developed for like crowds or like it was like navigating in crowd for humans. So it was for pedestrians because like they wanted robots to like walk along like, pedestrians. But here we are using it for vehicles. So the idea is that let's say we have a 3-vehicle scenario, we create a graph of the vehicles. So we try to model the interaction between them. And we also model the interaction over time. So there's an interaction between vehicle 1 and vehicle 3, but there's also interaction between vehicle 1 and vehicle 1 between different time steps. So they create this recurrent neural network over the graphs, and then they try to predict their locations in the future, the car's locations in the future. And then they use this prediction loss to optimize the framework. So this is basically the same thing, and I'm just converting it to a deep learning framework now. So I have these cars corresponding to gray nodes. So S1T is the state of vehicle 1 at time step t, and then over time step t plus 1, t plus 2. And then based on these data, I'm trying to predict their next locations. And the claim here is that the interaction with other cars will affect my next state. So they are useful for predicting my next state, and that's why we give input to this. Like this is a very like quick overview of the model. But the problem here is that this is saying my interaction with all these other agents will affect my next state, and that's not very realistic because I don't care about these cars here on the top left. They're just going in a different direction. They're very far away from me. There is like they tried neighboring attention, so they said if they are in my like close, it's like if they're close to me, then they're going to be useful. But that's also not true because, for example, this car on the left, I don't care about that car, whereas I care about these cars because if they, for example, turn left, then they will be in front of me. So instead, what we do is, or what we can do is, we can try to learn an attention module. This is like similar to the literature on computer vision. So in computer vision, they try to find the important regions of an image. In this case, we are trying to find the important set of cars that are going to be impactful on my trajectory. So I can learn an attention over these interactions, and that attention will tell me like which of these are maybe like more important, which of them are less important. And then like people said, okay, that's good, but again, we are not paying attention to all these cars. Humans' attention are sparse. So they said, okay, let's put some sparsity attention. And that's still problematic because, I mean, that's better than the previous one. But the problem is we can now have the case where our attention is changing very quickly between the cars. It's okay for an autonomous car, but if we are trying to model these other agents, these other cars that are human-driven, that's not going to be the case. That's not going to be the case. Their attention is not going to change this fast. So in fact, like cognitive science literature, they say human attention on different objects, it's usually changed slowly and smoothly. So in our work, what we did is we incorporated this into this deep learning model. So we added an additional loss term that will make sure the attention changes smoothly. So again, using the same architecture, now we have this like loss function. So the first one is just the same, like one-step prediction loss. We also added this sequence prediction loss, so it's not just the next time step that I'm trying to optimize for, but it's a sequence over some horizon. There's some regularization that is not important, and then there's this smoothness regularization. So theta here is the attention vector. So if we go back here, so thetas are the outputs of the attention network, and I'm adding some smoothness term over that, meaning I don't want this theta to change very abruptly between time steps. And that's like how we make this thing smooth.
This is theta hat.
Theta hat.
Theta hat is, yeah, theta is the attention that I have now. Theta hat is the predicted attention in the like unseen part of the trajectory, like in the future.
Oh, so you also attend to your prediction outputs of other agents.
So yeah, what I'm trying to do is, I'm the ego card. There's this other card, and I want to predict their trajectory, right?
Mhm.
So I need to model what they're attending to, and to do this in my loss function, I penalize these abrupt transitions between the attention. I'm also penalizing the abrupt transitions that I predict in the future. That's what theta hat does. So we tried, like we used this in some, like in this interaction data set. That's like some they have different scenarios. So in this case, it's a roundabout. They have a merging scenario. There's the intersection scenario. Like they have all these I think interesting scenarios. So okay, here are some results right away. Okay.
So these are from like AlgoVerse or Waymo type of data set?
No, it's the interaction.
Interaction,
Alex brought up
specific data
before.
set.
So they are like manually created or from some real world?
No, they come from payments. So it's a real data set.
Okay.
So here are some results. On the left, we are seeing the social attention model without smoothness, and on the right, it's our model. So what you are seeing is the green part is the trajectory that we observed, and then at some point we see our predictions of what's going to happen, and then the gray lines show what actually happened. So you can see that the social attention, it's very noisy. It's after like 2 or 3 time steps, it fails to predict future trajectories. Whereas with smooth attention, we are able to almost exactly follow the gray line for at least like 10 time steps.
But what about if you don't add the specific smoothness term in loss regularization? For example, if you're using only attention but without smoothness.
I think there's a yellow
That's the
one.
blue.
Right?
Yeah, that's left one.
That's
Yes,
the one.
smoothness like improves.
This is not social esteem, it's social attention.
Yeah, social attention is the one without smoothness. Ours is the one with smoothness.
But in comparison to the first work, that is social esteem that you are based on, how bad?
Remove attention to.
Yes, yes.
Okay. Yes, we have that.
Mhm.
Okay, so I'm going to come to that point, but yeah, again, similar results. So social attention again is going to fail after a few time steps, whereas ours go longer. Okay, and finally, there's the intersection scenario. This is social esteem didn't do that bad, but again.
But here you are like basically predicting everything as attending.
No, I'm not visualizing the attention. I'm not visualizing what they're attending to. I'm visualizing the locations the car will be in.
The
So the
prediction.
orange one is the prediction, and the gray line is the true one.
Why do you have multiple, I don't know, circles? It's multiple nodes here.
So it's like the smallest circle is the prediction for the next time step, and then 2 next time steps is the larger circle in a lot. So it's like we are predicting the next, like I think in this case, 4 time steps.
Mm-hmm.
So those show the next 4 time steps.
I see.
And so you're outputting just like a single XY coordinate as opposed to some like distribution.
We are outputting a distribution, and here I'm just showing the means.
I see. What distribution and like how do you sample from it?
Yeah, so it's just a Gaussian distribution. So yeah, here the output is that it's a mean and a correlation.
So like single hypothesis, there is no like multi-hypothesis.
No, I think no.
And the smoothness is like true most of the time, right? But sometimes something sudden happens? Like, does this have a relation to your phase transition definition? Like, is there
Yeah.
a way we can automatically detect these and like not penalize the loss or something?
Yeah, I think that's a good point. So it's true that in some cases our attention can change very quick. Like if it's like in a dangerous situation, like we can almost immediately attend to something else. I mean, of course, there's the reaction time, but like, ignoring the reaction time, we can almost immediately attend to something else. No, we didn't try that on that scenario because the interaction data set doesn't really have those kind of scenarios. We tried it on some like simulated scenarios, but like I don't want to claim anything on that because in simulated scenarios it's a much easier task. But I think it might be okay because this is just an additional loss. It's not like a hard constraint.
Yeah.
But yeah, we in our data set we didn't have like in our real data set we didn't have those scenarios. So it's hard to say anything conclusive.
Also the question, please could you please be a previous slide with losses? Yes, what was the main reason and motivation to add this sequence, in fact, because usually in the literature, the algorithm tries to predict only 1 point. 1 point, or maybe the whole future, but for example, not 4 and then 4 and then 4, as you said. And what was the motivation and how it influenced?
Yeah, I'm going to show some graphs about how it influenced, but the motivation is that so we are training on this interaction data set, and in interaction data set, let's say we have 100 time steps. So I can take maybe the first 70 as my training, and then I can try to predict the next 30, right? So the motivation was, why not use more data while predicting my model? So instead of just using the next time step, let me use next maybe like 5 time steps to inform the model, and then like we can do a window kind of thing.
Actually, this is it seems that it's based on the data set itself, the nature, because it has so long.
Yeah. I think in general these learning data sets, they have like I think long enough trajectories of most of the curves. So I would say I think in general it's a good idea to use sequence prediction loss.
So what do you think about attention as differentiating causation and correlation? Like ideally you want some like causal graph saying like this agent's paying attention to this one, but sometimes there's like third variables and other things that you can't really distinguish, right?
Yeah, that's true. This is like a deep learning model that tries to basically explain everything based on like attention and the location sensitivities of the cards.
Yeah.
So if there is an additional variable that is not in our model, it's going to affect both the attention and the predictions about locations. So I think ideally we should try to model them and like put them into our framework, but if not, it's hard to like remove them like from the graph.
Yeah, but I guess the issue is you can get problems where either there is a third variable that ties things together, or you have like you don't know whether A influences B or B influences A. You just see in the data set they're always correlated, right?
Right. Yeah.
I think the question is about causality.
Yeah. And whether attention has any problems with this.
We didn't observe any problems, but yeah, I can see that happening. So, in this case, we kind of have them affect each other. So it's like locations cause the attention distribution, and then attention distribution cause the change in location. So there's this like kind of like two-way interaction between. So ideally, like with enough data and like with expressive enough models, it should be able to model like both sides. But like if the model is not expressive enough, I don't know if that's ambiguity poses a problem. Yeah, that's a good question. So yeah, here here are some like quantitative results. So here, okay, ADE and FDE. So ADE is the displacement error in the like I think it's the average displacement error over the like rest of the horizon or the next, I don't know, 5 time steps. And then FDE is the displacement error for the final time step. So it's like far in the future how I'm like predicting it. So you can see that ours gets the lowest error. The others are something more interesting. So okay, the blue one is our original baseline. Our average is what you suggested, Alexander. So I basically remove the attention layer. I say I'm paying the same attention to all cars, and that's the light yellow one. And then there's ours non-smooth. So it's again, I use the sequence prediction loss. I have the attention, but I'm not putting the smoothness prior.
What is this difference from the social attention average?
You mean between red and social attention?
I mean, maybe between the yellow and the dark blue. Like,
right. Okay. So
isn't your baseline like social STM? What is
yeah? So our addition is smooth attention and sequence prediction loss.
Sequence prediction.
Yes.
Okay.
So in the social attention ones, they don't have sequence prediction.
Okay, so they only like predict the next.
Yes.
Right.
Okay, yeah, so the key takeaway of this section is, modeling other agents through their attention, it may improve our performance in multi-agent systems, and we have seen an application of this in autonomous driving. And yeah, with that, I would like to end by saying thank you to the collaborators in the works that I discussed today. And this was funded by NSF, TRI, and Future of Life Institute.
Thanks.
Questions? You can take that.
I think it's quite related to many of the things that we do
Yes.
internally.
For example, it's about the question about the querying. For example, when you're just providing some sort of data for human to compare. Suppose for, I don't know, for the real task like driving. Yes. How much do you think we need to show for humans to judge? How much do we need to provide them the number of pairs to compare? What do you think?
Mm-hmm.
The scale, the order, I don't know.
Yeah, I think it really depends on the complexity of the reward function that you are learning or the policy that you are learning. So, like if you and the good thing is you can so you don't need to generate like novel trajectories because you already have these driving demonstrations. You can ask users to compare the existing demonstrations. So you can take clips of these different driving trajectories and you can show them to the users and you can ask them to select. But I think they're going to be interesting like research questions there. So one of them is, for example, like how my preferences are going to be affected when I just watch them versus when I experience them in a car. Like because they're like, I think, implicit preferences versus actual preferences. Like when I watch things, I can be like, oh, this is stopping in a stop sign for 3 seconds. That's very like it's obeying the rules. It's great. I'll choose that. But if I'm in a car waiting at a stop sign for 3 seconds, it's just too much, and I'm not going to like it. Right. So there are all these problems. But yeah, in general, you can directly use demonstrations to generate the comparison questions, and that's good. The number of questions, though, as I said, it really depends on the complexity of the reward function, and it's hard to say. But I don't think you need a data set that's dominantly comparisons. Whereas in robotics, we needed that because a lot of biases affect how humans give demonstrations. Whereas in driving, I think humans' demonstrations are closer to optimal or near optimal demonstration. So I think a small number of comparisons may help fine-tuning the reward function. Like you don't need dominant comparisons data sets.
Okay, thanks. Also have the question in our chat. How do you deal with cases where the comparisons are inconsistent?
Yeah,
We went through it.
Okay, so yes. So,
yeah, I think you were
sorry.
talked about that.
So the attention work,
When I was
is that similar? I mean, like, there's a people also like sing transformer, right? Like, there, I mean, transformer you also like some kind of like attention. Is that some connections or how do you compare?
That is true. So the architecture that we use is not a transformer, but yeah, we have these like LSTM over graphs, and then we are learning an attention over it. So I think the underlying ideas are similar, but yeah, architecture-wise it's different. Like this, we started this work before transformers became popular. But yeah, I think that's also interesting, like because yeah, it's like I think the architecture is different, but the ideas are similar enough that we could try to use transformers.
So do you have ideas for more specific evaluation metrics for this kind of attention modeling work, other than just like, did my prediction error improve, or like?
Yeah, we discussed about this at some point. I think we could have like additional helpful measures. Like if we had a, for example, eye tracking system in the car, then we would look at where the driver looked at in the past, I don't know, 2 seconds. And then we can say, oh, they are paying attention to this and this. And then we can try to maybe match them. Or like we can use it as a loss. So that would be another metric. Yeah, well, I think another that would be more useful is, so here we are only measuring the performance on trajectory prediction. But the ultimate goal is to use these trajectory predictions for optimizing our own action. So an ultimate evaluation metric would be how efficient and safe I'm driving based on the predictions that I make with this approach versus with like social SDM. Yeah, this attention modeling work it's very new. So it's like, it's in ICRA, so we are going to present it in like 2 hours. So I presented it for the first time before the conference here. The actual presentation is in 2 hours.
Oh, so it's like virtual friend.
Yeah, it's virtual. Yeah. I mean, so some of my co-authors are already in New York, but I'll be virtual.
Jonathan, who's on the call, is there right now.
Oh, okay.
I will be sure to listen to it.
That's good, yeah. Zhangji is going to present Zhangji Zhao.
Cool. I will look for the paper.
I also saw that you have your work also have like a lot of this altruism reward stuff, like you didn't maybe touch.
Yeah,
like this multi-agents.
Yeah, the macroscopic network routing. Oops. Now. Uh-oh. Okay. I messed up. I enabled subtitles and then died. But I'm
Instantly.
God bless. Okay. I wanted to go to a slide, but okay. So yeah, there is, okay, maybe I can talk about this here. So it's like, yeah, in that kind of work, what we do is we have a like traffic network, and then cars are trying to go from some origins to destinations, and we have a fleet of cars that we can control. As I said, maybe like we are Uber, we are Nuro, we are like Lyft, and we have a fleet of cars that we can decide which routes they are taking. So the idea is, if everyone tries to take the shortest route, it's going to be congested, and it's going to be bad for everyone. Whereas if some cars take some longer roads, then things will be better for everyone, including themselves. So how do you optimize for that? This is like the general problem in dynamic traffic assignment. And the altruism comes into play because, as I said, some cars will have to take the longer route, so they have to be altruistic. They'll not behave selfishly. So in that case, like we connected it with like learning from comparisons, and what we did was again, like let's say an Uber, and then Uber gives passengers an option to like wait for 15 minutes and pay less. That's an option in both Uber and Lyft. Or you can pay more and just take an Uber right now. Based on what you select now, they understand, they learn your price latency trade-off. And then we showed that, like in concept, they can use this information to better optimize their prices so that they can minimize traffic congestion. The problem is they don't have any incentive to do that. Like, why would Uber care about minimizing traffic congestion? Hopefully they do, but there's an incentive design problem. Like we need incentives for these companies to like shoot for minimizing congestion, but that's the missing part.
I see.
Thanks.
Yeah.
So thank you.
Thanks.